Well, I thought it would be interesting to get a Z80 CPU, just the old Z80 processor, stick it on the oscilloscope and see what interesting signals came out of its pins. So here are some CPUs, some Z80 CPUs that I found laying around on my bedroom floor. And here is my oscilloscope. Thanks very much, Banggood. So let's link the two together and look at some wiggly lines. Now, of course, in order to do that, I've got to have some power and a circuit and all that kind of thing. So here's my Z80 playground. I've plugged the Z80 in right here, and I've got my oscilloscope. I'm going to connect it up, and we're going to take a look at what comes out. So to make this possible, what I've done is soldered on a wire directly onto one of the pins of the Z80 here. That's the clock pin, so we'll have a look at that on the, no, we'll have that, yes, we'll have that on the yellow channel. And on the blue channel, I'll start off actually, instead of looking at the outputs, we can look at the inputs. This is the clock section here. This is making the 10 megahertz clock. So I'm going to have a look at what comes out of the crystal and what's then going into the CPU. So obviously the clock's the most important thing for a CPU to actually, it's not going to run without a clock. And look at, so the yellow trace at the top is the clock signal. The blue trace at the bottom is the kind of curvy sine wave sort of thing coming out of the crystal oscillator. And what can we see from that? Well, firstly, that's not a very square wave. In textbooks, square waves are square. In any circuit I've ever made, square waves are not quite square, but that's particularly bad. That's almost a Batman logo. Now, obviously, if you're going to see anything happening on a CPU, the CPU's got to be running a program. So what I've done is written the world's most simple program, which just does nop, 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 and jump back to the beginning. So at location 0, we've got a no operation instruction. In fact, we've got 3 of them, and then we jump back to location 0. So what that will do is it will keep the CPU busy doing a sort of pointless loop while we look at the traces that are coming out of it. So I have connected up the yellow trace to the clock and the blue trace to the M1 pin, the M1 output of the CPU, which I've got actually on the Z80 playground. All the pins from the Z80, or a lot of the pins from the Z80 are available on this edge connector down the bottom here. So if I connect up to that, you can see that the M1 is an output that goes low. And what it does is it goes low on the first part of the fetch, decode, and execute cycle of the CPU. So what happens is that when the CPU goes to run an instruction, it does it in various different stages. So it's not one clock cycle per instruction. It actually takes 4 clock cycles for even the simplest instruction to get executed on the Z80. If we zoom out a little bit, we can see that my program, nop, 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 jump to 0, is highlighted here. There are 4 instructions running, and the bottom trace, the M1, goes low for the first part of each of the instructions. So it goes low for the first no operation, it goes low again for the second one, low again for the third one, and then low again for the jump. And the jump is a long instruction, which is why that instruction is longer than the others. And then we go back round to no operation, looping round. If we compare the M1 to the clock cycles, we can see that there are actually 4 clock cycles per NOP instruction. So it takes 4 cycles to do absolutely nothing. And M1 is low for the first 2 of them, and then it's high for the second 2 of them. And the M1 seems to be always low for 2 clock cycles, no matter what instruction you're executing. Measuring this, so if I put the measurer on there, for the 4 instructions, that is taking 2.19 microseconds to do the 4 NOP instructions and 1 jump instruction. And this shows you that actually for speed optimization of Z80 programs, the length of instructions is quite critical. And it's often surprising which instructions take longer than others. So for example, if we change that program, so instead of jump to 0, like an absolute jump to location 0, we do a relative jump back to the start of the program, assemble that, put that into the ROM of the Z80, and then try that again, we see this time that the the jump relative is a slightly longer instruction. So I've left the markers in the same place on the screen, but you're seeing now 3 no operations and then a jump relative. And I think the reason it's longer is because we have to get a number and then do some arithmetic. We basically have to add -6 or whatever the relative jump is to the current program counter in order to jump back to location 0. So it takes actually slightly longer. And if I just move the measuring cursor on the oscilloscope, we can see the amount of time that it takes to do this. And the answer is 2.405 microseconds. So it's slightly longer to run this program, which does exactly the same thing. And so it's quite common in assembly language that you can find several different ways of doing exactly the same thing. Okay, so now I want to look at the refresh pin, which is on pin 28, which is up here. So if we look on there, we can look at the refresh pin, which is an output that the Z80 produces. And it's a bit of an odd one, this. Refresh is used by the processor to refresh dynamic RAM. So in the olden days, when people used dynamic RAM, they needed the refresh output. This, of course, on my Z80 playground, this is static RAM, so it doesn't need the refresh output, but I thought it'd be quite interesting to take a look at it. And interestingly, the refresh pin seems to have an output that goes low pretty much 2 clock cycles behind the M1. It seems to do exactly what M1 does, but 2 clock cycles behind. I can't think of any application at all for the refresh pin, but I thought it'd be just interesting to take a look at it.